And here we go. Alrighty, well, thank you guys for showing up today. I really, really appreciate it. We're going to go ahead and get started with the CHEM223A Introduction to Infrared Spectroscopy. Now, this is a dry lab because we do not have any projects for you guys to really do for this lab right here. It's really conceptual. We're going to talk about the theory behind infrared spectroscopy. We'll talk about why we do it, and then we're going to actually learn how to read the spectra. The spectra, at first, when you take a look at it, kind of looks like a squiggly line, and you look at it and you're like, I don't know what I'm looking at. I don't know what this is, but by the end of this presentation, you're going to look at a spectra and you're going to say, oh, that's an alcohol. That's a carboxylic acid. Oh, there's definitely an amine with two hydrogens in this molecule. And that's really the cool and powerful thing about infrared spectroscopy is that it lets us see what exactly our molecule is. You know, atoms and molecules are so incredibly small that we can't really see them with the naked eye. We have to use tools and instruments. So let's go ahead and get right into it. So spectroscopy, which is what we are studying today. It's a Latin word. It means spectro, image, and scopy, to look at, or scopy, like the telescope, you look at something. And so really, we take an image of an absorption of a molecule or a reflection or a diffraction, and based on the image, it gives us information about the molecule. So you can see in this slide, we show you the electromagnetic spectrum. I'm sure it's not your first time seeing it. Basically, we have electromagnetism, one of the four fundamental forces of the universe, and this is carried by a photon. So what we perceive as color, we call that visible light. You see there you have the rainbow colors right here from red all the way to blue, Roy G. Bibb, right? And you can see it's really just a very small fraction of the entire electromagnetic spectra. Our instruments are our eyeballs. So with our eyeballs, we can detect the colors around us. And you will learn later on in organic chemistry that colors are actually determined by bonds or electron transitions. It's really cool. But we also have other spectra that we cannot detect, such as ultraviolet light. That's the one that gives us our tan and our sunburn. We have X-rays, which is what allows us to see through our bones when we go to the dentist or when we go to the doctor. We have gamma rays, which is what turns Superman into, super powerful man. Also, if it damages your DNA, so don't try to become a superhero. Gamma rays will kill you. And then, of course, cosmic rays are anything in that range of extremely high energy, high frequency, super short wavelength electromagnetic waves. That's what gets emitted by the black holes, like near the event horizon. We don't have the technology to produce waves that strong down here on Earth, thankfully, so we don't really have to worry about that. And then on the opposite end, to the right of red, you have infrared, which means below red, right? You have ultraviolet above violet, infrared below red. And infrared radiation we do perceive as heat. So every time we are near a campfire, that fire emits a lot of infrared photons. Those photons vibrate the molecules in our skin and our nerves, and we feel that as hot. And that is why we feel heat with infrared. We also use it to open your garage door. We use it to open your car when you have the little keyless startup or whatever. And then you also use it for TV remotes. So infrared radiation is very useful. We perceive it as heat, and we are also going to be using it to look at molecules, specifically the vibrations of the bonds of the molecules. That was one of the questions in your pre-lab quiz. What do we measure? We measure vibrations. It's infrared spectroscopy measures the vibrations of the molecules, but more specifically, the vibrations of very specific chemical bonds. And so we will talk about that throughout the presentation. Some of the waves we use to cook our food, microwaves, they're called microwaves because they are actually about a centimeter to about a foot long. You know, they're considered very large. That is also why if you have seen the video where you put the grape in the microwave, you see that it starts emitting a lot of electricity. That's because the size of the grape is the same size as the microwave, and so it causes a whole bunch of interesting physics and chemistry to be happening there. We won't talk about that, but the point is microwaves are fairly large. And then even larger are radio waves. Some of you guys have been looking at the instrument in the hallway where we do our TLC ultraviolet thing, and you've asked me, what is that back there? That is an NMR spectrometer, nuclear magnetic resonance, very similar to the MIR, whatever, MRI. There you go. Sorry, MRI that you take at the hospital. That uses very much the same technology as NMR does as well, and that is done using radio waves. They shoot radio waves at a sample, and the molecule that has hydrogen or carbon, depending on the radio wave frequency you're using, it will show you the spin and therefore the chemical environment of hydrogen and carbon atoms. So we use pretty much the entire electromagnetic spectra. We perceive only a small portion. We call that visible light. We know its relative physics. The speed of light is a constant, and you can get that by multiplying the wavelength and the frequency of a wave. Also, you can calculate the energy if you multiply the frequency by Planck's constant. But this is physics, so if you want to know more about it, you will either have already taken physics, or you can always take physics, or you can watch some cool documentaries on YouTube about it. But the point I want you to get from this is that out of the entire electromagnetic spectra, we are only using the infrared, specifically 780 nanometers to 1 millimeter. That was also part of your pre-lab quiz. That was the answer. They are a little bit lower energy than red light. We cannot perceive it with our eyeballs, but we can feel it, the photons of energy. And not only can we feel it, the molecules, more specifically the bonds of the molecules, can also feel it. But we'll get into that. So how exactly do they feel it? What is happening at the atomic level? Well, in Chem 111A, we talked about how if you shine a photon of a specific energy at an atom, depending on the amount of energy, and it has to be a very specific amount, that electron will jump, for example, from n equals 1 to n equals 2, or n equals 1 to n equals 3. And then once it gets up there, it'll also come back down, and when it comes back down, then you will have a release of another photon of that same energy. So this is kind of an abstract concept. You have what's called the low energy state. So for example, us, when we wake up in the morning, we are in our ground state. We are not moving. We have not used up any energy. We are just in the most possible lowest energy state we can be at. And then to get up out of bed and go to work and go to school and drive and think, we have to put in energy to get us to the higher energy state. Electrons have energy states. I mean, they're not anthropomorphic like human beings, but you can excite an electron from a low energy state to a higher energy state with exactly the right amount of energy. And that's the thing. It has to be that specific amount of energy. If it's any higher, it will not be absorbed. If it's any lower, it will not be absorbed. It has to be that specific difference in energy between the low energy state and the high energy state. And there's various states. We have what are called electronic states. That is what we learned about in Chem 111A, where you can take an electron from n equals 1 to n equals 2, or n equals 1 to n equals 3. But you also have what's called translational states. In other words, heat. The fact that when you heat up a gas, the molecules move around a lot quicker. That is a form of absorption of energy. It's just that that absorption of energy becomes a movement of the molecule across space. And then for IR, we have what's called vibrational energy. And what this means is that you can think of the chemical bond as a spring with two masses on the outside. And if you have ever played with a spring, you know that you can compress the spring and you can elongate the spring. And if you grab one end of the spring, you could also wiggle it and twist it and whip it and turn it and all sorts of different sorts of motion. Those are called vibrational energy states. And then finally, we also have rotational energy states where the molecule itself is just rotating. It could be rotating left to right to left, up to down, 90-degree angle, all sorts of different states. So in this case, electromagnetic radiation can contribute to different types of absorptions, whether translational, whether electronic, whether vibrational, whether rotational, depending on its energy. And infrared radiation specifically does the vibrations of the molecule. And so this is just basically what I was telling you guys. If I can go back a little bit, sorry about that. That basically high energy light, ultraviolet light, X-rays, things like that, that causes higher energy excitations. Electrons require high energy to go from n equals 1 to n equals 2. So usually we use a longer wavelength to do that kind of thing. Lower energy does more of the space translational, rotational, vibrational, like microwaves. Microwaves vibrate molecules of water in your food, and that is why your food gets hot. And that is also why if your food doesn't really have a high water content, you're not really going to heat that up because the microwaves work by vibrating the molecules inside your food, specifically the molecules of water. So this is physics. Again, this is kind of just like the background that we need to understand what exactly IR is. It's not often that we stop and think about the nature of the electromagnetic spectra, so it's a good idea to kind of get into the little details. This is good to know. I recommend that you know it, but you don't have to know it. You're not going to be given like a delta E equation and plug stuff in. But it's still a good idea to know what the equations mean and what the trends are. Higher energy, lower energy. Ultraviolet light is higher energy. Infrared light is lower energy, things of the sort. And so this was just what I was talking about earlier. Depending on what sort of analysis we want to do, we pick our frequency, and that gives us specific information. So NMR, like I mentioned, uses radio waves, and that tells us where the carbon and the hydrogen atoms are in a molecule, chemical environments. If you take 223B next semester, or if you go to 320L, you guys will do NMR spectra. And if you decide to major in chemistry and become an organic chemist, NMR is your life. You basically do any NMR at every single step of a chemical synthesis. You make your molecule, you do your chemistry, you do your TLC, and then once you do that, you purify it. Once you purify it, you take it in the little tube, you put it in the NMR, you have a spectra. You're like, yes, I succeeded. I'm gonna move on to the next step. That's what it's for. You can also use IR. IR is a lot cheaper than NMR, and more places can afford to have an IR spectrometer, and IR will tell you the functional groups that are present. So, for example, if you're trying to make a carboxylic acid and you do an IR spectra and you don't see the carboxylic acid signature, you know that something went wrong and you have to go back and do it again. Or maybe you selected the wrong spot in your TLC. So this is why we do spectroscopy. It gives us information. And finally, we have another type of spectroscopy that does use ultraviolet light and visible light. We call that UV vis or UV visible. And this tells us about conjugated pi systems. A conjugated system is an alternating single double bond. So you'll have a double bond, single bond, double bond, single bond. We call that in organic chemistry a conjugated system. Double bonds have pi bonds, so it's a conjugated pi system. It's just a fancy way of saying alternating single and double bonds. And you saw that in TLC. When you did your TLC and you shown the UV light at your plate, you saw the dark spot. That is because the molecule acetylsalicylic acid or acetaminophen is absorbing that UV light because the ring is aromatic and it is an alternating single double bond delocalized system that happens to absorb a photon of the same energy as ultraviolet light. So we see these things. We see these things every single day. We just don't think about like the physics behind it. But all sorts of ultraviolet light, all sorts of electromagnetic light gives us all sorts of different spectroscopy. And just yesterday, I just found out that we can actually do X-ray spectroscopy. Every element emits its own signature. So if you take a compound and you shine X-rays on it across different wavelengths, you can actually tell me the exact percent composition of elements in that compound or molecule or sample of matter. I did not know we could do that. That's completely brand new to me and it's blowing my mind. So the point is that spectroscopy is really like its own little field. You can go and do your PhD in spectroscopy. There's jobs in spectroscopy. You're called a spectroscopist, and you have basically whatever specialty you want to do. The more you learn, the much better paid you will be. This is one of the few specializations in science that actually pays off and pays really well. So just stuff to consider. Are we okay so far though? Everything good? Like, are you guys no questions, no nothing? All right. Yeah, again, at any time, if you have questions, simply let me know. More than glad to answer the questions. So now that we've talked about electromagnetic radiation and electromagnetic spectra, let's focus in a little bit more. Infrared spectroscopy. Now I can focus strictly on infrared. Remember, 780 nanometers to 1 millimeter. That is the range for infrared. Not exactly, right? A little bit plus minus 200, 300, but generally that is well defined. And so this is emitted by an instrument. We do have one. Some of you have seen it next to the UV lamps. It's very tiny. I will show you a picture in a bit. And this instrument basically takes the sample and shines the IR photon into the sample. And that causes the sample to vibrate. And then we measure different wavelengths on the x-axis. And we try to see what percentage of light goes through. And then we take a measure of that intensity. And depending on the functional group, different functional groups absorb with different intensities and with different wavelengths. And that creates a fingerprint that allows us to properly identify what bonds and what functional groups are present. It doesn't tell us how many, it doesn't tell us where it is in the molecule, it just tells us it's there. The bond is present and it is absorbing infrared light. And so again, like I mentioned, if you have taken physics, you will have learned or hopefully have heard of something called the harmonic oscillator. That is just a very fancy way of saying a spring. A spring oscillates in and out, compressing and stretching. And then if you attach masses at the end, you can have different intensities of vibrations, stretching, and compressing. So you can see in this slide right here, you have the HCl molecule. Well, hydrogen has a molar mass of 1 gram per mole, and chlorine has a molar mass of 35 grams per mole. So you basically have a very heavy object anchoring a very light spring. When it vibrates, it's mostly going to have this motion rather than a symmetric motion. And all molecules vibrate. I want to emphasize that because up till now in chemistry, we have basically been showing you pictures of molecules just like, hey, this is a molecule in terms of atomic composition and atomic structure. But this is a 3D world, and in the real world, things are always vibrating. So all those hippies were actually right. Like, it's all about vibrations, man. It really is. It really is. It's all heat. It's all vibrations. It's all electronic vibrations, rotational vibrations. You name it. It really is all about vibrations. In this specific case, it's about a spring-like vibration between two atoms in the form of a chemical bond. And sometimes it happens symmetrically. It means like an accordion. Sometimes it happens asymmetrically, where one side is heavier than the other. Sometimes there is a wiggle where the molecule is kind of circling around like a helicopter. And sometimes there is a twist even. Like some double bonds will get slightly twisted without breaking. And that is another form of vibration that absorbs its own frequency of energy. So this is basically what creates our infrared spectra. We have a different wavelength on the x-axis, and depending on what bonds are there, you will see when they absorb and when they vibrate. So does that make sense? Like, are you guys okay with the idea of thinking of chemical bonds as springs? That is the whole key to understanding why infrared spectroscopy works. That makes sense? You can just put thumbs up on the Zoom. At least I know you're alive. Awesome. Okay, I see a few. Thank you guys. Thank you. Alrighty. Cool. Okay, so continuing on. Hold on. I accidentally pinned. There we go. Alrighty. So moving on, moving on. Here's the actual instrument you see right there. It's the blue small box that we see in the lab. There's a dot right here in the center. You usually take your sample, you dissolve it in acetone, you take the Pasteur pipette, and you dip the solvent into that center right there. And then you take that little screw at the top and it basically squishes. That's the detector. And then that dot emits the IR radiation. And then it starts at a one wavelength, 780 nanometers, and it goes all the way to 1 millimeter. And then it measures what percentage of the infrared photon radiation went through. It's the percent transmittance. What percent got transmitted? And so instead of measuring in nanometers, for some reason, I'm sure it's historical, maybe the inventor, something about convenience. I'm not exactly sure. You can always do your own research. We measure things in something called a wave number. So you see right here, we have this V symbol and with the bar on top. That is what's called wave number. That is what we are going to be plotting on our x-axis. And to solve for that, you take the reciprocal. It's 1 divided by wavelength equals wave number. And instead of nanometers, it's going to be in centimeters. And then the energy you can always calculate. Remember, energy is just Planck's constant times frequency. So you can plug it in. The wave number would simply be Planck's constant times the wave number times the speed of light. And remember, everything has to be converted to meters for it to properly work. And it is directly proportional to energy. So the higher the wave number, you see this the spectra right here on the bottom right. The higher the wave number, the higher the energy. And the lower the wave number, the lower the energy. I think it's pretty straightforward, right? Low number, low energy, high number, high energy. And so it goes from 400 wave numbers to 4,000 wave numbers. And notice that the units of wave numbers is in centimeter to the -1. And then you can see here on the y-axis of the spectra, you have percent transmittance. What percent of the light went through our sample? You never get 100% because there's always natural, what do you call it? Diffraction? The thing where the light goes in and it gets a little bit bent. I think it's diffraction. I think I'm using the wrong word, but there's always some sort of deflection, some sort of bending of the path of the energy of the light. So you never have true 100% transmittance. But you can see that in some portions of the spectra, you have more intense absorption, meaning lower transmittance. So for example, if you look at the number around 3000, you will see that its transmittance percent is about probably 5. I think that's 5% transmittance. That means that 95% of that photon got absorbed by the sample. And so that is referred to as high intensity. The peak has high intensity, low transmittance, high absorption. And you can see in other parts of the spectra, you don't really have a lot of absorption, so there's very high transmittance. And so you see the bottom point, it says that most bonds in the organic molecules are between 400 to 4000 wave numbers. And that is why we choose the spectra. Remember, we're going to be thinking of these bonds like springs. And it is these springs that are going to vibrate, and the vibration is what absorbs that energy. The energy gets absorbed from the photon to the bond in the form of a vibration. And so I'm going to stop sharing this screen right here for now so that I can show you guys exactly what that looks like. I think this will be a good point to show that. So let me go back to the Google tab, and I will begin by showing you the vibration of water. Okay, so here we go. So this is a really cool website. I recommend you guys bookmark it, especially if you're going to stay in chemistry. I have been using it since I discovered it probably about 7, 8 years ago. Really cool three-dimensional model. See, you can get the molecule, you can rotate it, vibrate it. You can use it for organic, inorganic. You could use it for X-ray diffraction, like I'm using it right now. It's really cool. For me, molecules are more alive when we can actually see them. So in this case, you go to structure and bonding, and you can see right here, it says molecular vibrations IR. I clicked in water, and this came up right here. And I can zoom in and I can zoom out. So what I'm trying to show you guys is that water stretches in 3 different ways. It goes symmetrically, so the bonds, remember, the bonds are springs. So the bonds are springing into the oxygen molecule like this. We call that a symmetric stretch. And that has an associated frequency because remember, the spring is going up and down and the waves go up and down. So that has an associated frequency with it. And that absorbs a specific frequency of infrared photon. And then you have another type of stretch. For example, you see here the anti-symmetric stretch. That one is kind of a little lopsided, and that has its own associated energy. And then you have another type here at the bottom, it's called a bend, where the molecules, instead of like stretching in and out, remember, springs don't just go in and out. They can also wiggle and twist and be bent in all sorts of different ways. So in this case, you're kind of having like the little wrist cruncher that those dudes use at the gym. It kind of just squeezes in. We call that a bend. And it is a symmetric bend because it happens at the same time. The cool thing about this website is it can actually show us these movements right here. So what I do is I go to controls and this little menu here pops up and I simply click next. And you can see right there, there is the water bending. This is what happens in the real world when you shine an infrared photon at a molecule. If the molecule is infrared active, it will absorb that photon and begin to vibrate at the associated energy. And this is why molecules are able to give us specific fingerprint spectra when we use infrared spectroscopy. Does that make sense? This is the key to it all right here. Like, if you get nothing else from IR, you should at least know that the molecules are vibrating, man. It's all about the vibrations. Okay, so this is the bend right here. You can click next. And you see here's the other one. This is the symmetric stretch right there. You can see it's kind of like flexing its atomic muscles. It's just like, heck yeah, let's go and do back day today. And then you have the other one over here. This is the asymmetric one. This is more of like that, you know, the dance that Trump likes to do. He's just constantly going like back and forth like this. And so depending on how many bonds you have in a molecule, and depending on the symmetry of the molecule, and depending on the types of atoms in those two bonds, the difference in weight, and also we will find the polarity of the bond, you can have all sorts of different factors that contribute to your infrared spectra. So this is water. Let's go ahead and try something a little bit um, more bonds. Let's try methane. Methane has 4 bonds to a single, it's carbon-hydrogen bond. So here you go, you see methane. And it doesn't show a diagram on the right side, but I can still play the vibrations. If I go to controls, this menu pops up. I'll click next. So here's one type of vibration. I unfortunately don't really know the name, but this looks like a very excited dog waiting for treats. So it's like, come on, give me treats. I want treats. So there's that. And then over here, you have also a very similar one, but instead of the bonds going this way and compressing, now they're being stretched out this way. So this you can consider this like the yoga dog or whatever. And then here, another one. See, now you have a different axis that the vibration is happening in. And then over here you have like kind of like a weird like twist. You see this molecule is twisting. It's like twisting its torso back and forth. And so you can see that because methane is a more complicated molecule, it has a more complicated infrared spectra, right? It stands to reason that the more complex the molecule, the more bonds, the more possible twists and stretches and bends and compressions that these molecules can have, and therefore the more complicated the spectra is going to be. But also, good news for us, just because it's complicated doesn't mean it's bad. It means we get a lot more information about what is in there. Oh, look at this one. I wish somebody did this to my back, the Mr. Incredible stretch. It's just like, just snap the whole thing. This also is a vibration and it has its own energy. And all of these are happening at the same time. That's the part that blows my mind personally. Look, you can click right here, show all vibrations. And this is what a molecule of methane, this is how it moves in the real world. It's happening all at once because the sun is shining a full spectra of all sorts of ultraviolet light, X-rays, gamma rays, all sorts of the electromagnetic spectra are coming out away from the sun, but the atmosphere filters most of it out. And thankfully, we've evolved to only perceive visible light and also to not be killed by UV light or infrared light. We don't get cooked. We do get, skin cancer if we're out in the UV light for too long. But in short, this is all happening all at once. The molecules in the real world are always vibrating like this. This is why things feel hot. This is why things feel cold. This is why things expand when they get heated up because you're taking up more space by these vibrations. So it's like a paradigm shift I want you guys to make in your minds because up to now we've seen flat molecules. They're not flat. They're moving around. Their bond is not a single length. It's constantly changing in length. It's just the average that we measure. It's just at absolute zero, at standard temperature and pressure, like we have these specific conditions. But the molecules are vibrating, man. I cannot emphasize that enough. The molecules are vibrating. So let's look at one more. I want to take a look at benzene. Let's do benzene. Benzene has 6 carbon atoms and 6 hydrogens, right? So again, you go to controls, and then you can click next. And here you have like a little very subtle twist. Notice how the twist is not that intense. I actually want to emphasize that right now. The twist is not very intense. That's because there's double bonds here. The double bonds are stronger than the single bonds, and they're also shorter. So again, if you've ever played with springs, the longer springs are usually thinner, and they're usually very weak, and they usually wiggle around with very long wavelengths, and thus lower energy, right? But if you've ever played, for example, I hope not, but with garage springs, never play with those are very stiff. They have a lot of pent up potential energy, and it takes a lot of external energy to make those even budge a little bit. Same thing with the shocks in your car, right? Your car is like 2,000 pounds, 3,000 pounds, 4,000 pounds. That's how much weight it takes for the energy to compress the springs in your shocks. I don't think a human being, unless it's really bad shocks and they're like really worn out, I don't think a human being could take the shocks and compress them with their own strength. You need a lot of energy to compress stiffer, shorter springs. And you could think of the double bond and the triple bond as stiffer, shorter springs. And so you see here that the twists are not as intense as methane because double bonds do not freely rotate. We learned that from lab 1, remember? So this is one example of one sort of motion. This is another one. Again, you see that the twist is not that intense. And then here you kind of get like a little wiggle, like a little like just jam into in a jazz club waiting. And then here you get like another one. And here you get like, this is called out of plane bending because the hydrogens are bending up out of the plane of the benzene. And so here we have another one, asymmetric out of plane bending, also its own associated energy. Here we have like a symmetry, half of the molecule is bending up out of the plane, half of the molecule is bending down out of the plane. And then here, only 4 of these atoms. You see the symmetry right here? So again, symmetry also matters, but there's a whole class you can take on that. I'm not going to get into that, but it's really cool. Symmetry plays a very big role in chemistry. And then here you have kind of like an inward stretch or compression, if you will. And then here you have this like turtle swimming motion. And then, yeah, I don't know what this is. But you see, there's a lot. And again, if I show all vibrations, you see the benzene is just wiggling around, vibrating, constantly moving around in all sorts of directions and ways. caused by all sorts of electromagnetic radiation, specifically infrared radiation that is constantly being bombarded into the molecule. So this is the real world. This is the universe that we live in. I hope I drove the point home because without these visuals, IR is just another thing that you read about, and the lines are just another boring graph that you see, and it honestly doesn't mean anything. This, in my opinion, is what makes the IR spectra comes alive. So if you are curious about this, you can go on CHEM223A. You can click where it says structure and bonding, and you can see all sorts of information visualized. Really cool website. I highly, highly recommend it. There is another one I wanted to show you. This is the Purdue vibrational modes of small molecules. The models are a little bit outdated, but you can still see them all summarized. So for example, ammonia, you can see here, you can see all of the vibrations of ammonia. And the cool thing about this specific website is it tells you where exactly, what wave number you can find these motions of these molecules and whether they are IR active or not, and also its relative intensity. And so you see here it says Raman active. So these are the vibrations of the bonds of the molecule. That is infrared. Rotational states of energy, that is called Raman spectroscopy. But we don't talk about that here. That's physical chemistry. You can take it a class or you can just watch a YouTube video about it. But sometimes you will do an IR spectra and your molecule will not be IR active. Now you have to go to the Raman spectrometer and then measure its rotation instead. But most of the molecules we're going to be looking at are in fact IR active. So we don't really have to worry too much about that. But this is another website, chempurdue.edu, and you can click on all sorts of molecules and you can see all of their vibrations and how they move around. And so again, all molecules are constantly vibrating. That's the point. Hopefully, like I mentioned, I drove that point home. I'm going to stop sharing now, and I'm going to go ahead and go back to the presentation. In the meantime, are there any questions about what I just talked about? Like anything that you guys want to clarify? Okay. Alrighty, again, at any point, go ahead and let me know, and then we can always get to it and ask questions. So let me go ahead and do from current slide. Let's see, there we go. From current slide, I was right here. There you go. Okay, so we are now back over here. So now, hopefully that you've seen those images, when I show you this spectra, again, the intensity where the peaks are strongest, that is where one of these vibrations is happening. That's what I want you to perceive. When you see the high intensity, you need to think there is a vibrational mode happening there. The question is, which one is it? So we're gonna get to that next. So again, why do we use IR? I already told you guys, the whole thing I just showed you was basically this. Every molecule is unique and every molecule has its own number of vibrational states, and therefore every molecule has its own fingerprint spectra. That's generally it. There's not really much more that I can say about that. And because molecules are made of functional groups, we know what functional groups are there. And so like I was mentioning, there's lots of things that allow us to see whether these things are going to be perceived in IR. One of the very important things that needs to be noted is that it needs to be a polar bond. So remember, symmetry plays a big role. H2, you just have two hydrogen molecules connected by a spring. You can see the symmetry in the middle. There is no change from the perspective of the instrument. Everything, the distances never change because they're always the same away from each other. It's symmetrical. The masses are the same. As far as the instrument is concerned, it does not exist. So all of the diatomics, hydrogen, nitrogen, chlorine, fluorine, you cannot see that in an IR spectra. It has to be something like a CO bond, like an ICL bond. Carbon hydrogen is polar. Carbon is more electronegative than hydrogen. So even though we consider it a non-polar bond in Gen Chem, it is still a polar bond, and you can perceive that with infrared spectroscopy. And so the more polar the bond, the shorter the bond tends to be, and therefore the higher the energy that it needs in order to vibrate. So increasing polarity increases intensity because you need to absorb more energy to vibrate. And that's just the gist of it. The more you eat, the more energy you have. The more energy is shined on a molecule, the more they will vibrate. And if the molecule is a very strong bond, then that bond requires an equally strong amount of energy. Everything is related. So increasing polarity leads to increasing intensity. That is the gist of this slide right here. And this, again, this is what they were going to show you. They wanted you guys to visualize it. I already showed you how these molecules bend, and they all happen simultaneously. And then it says here, stretching vibrations occur at higher frequencies than bending vibrations. Yes, it is easier to take a molecule and bend it than to simply compress it like an accordion. So vibrations will generally be higher energy than bends or twists. At some point, you talk about IR so much that you kind of just throw the words around freely. People kind of know that you mean vibration. So if I say stretching, but in real life it was bending, don't get mad at me. The point is they're still moving, man. They're still vibrating. So that's the point that we're trying to make. And just like I mentioned as well, if it is symmetric, for example, carbon dioxide is symmetric, because the change in the dipole is the same no matter what, there is no actual change. It's not really IR active. So some stretches are IR active. So you can see the asymmetric stretch that will make one oxygen closer to that carbon. That changes the dipole in this direction, and that'll also change the dipole in the other direction. So there is an overall change. It's an asymmetric change. You will see that stretch in IR. But the symmetric stretch, because it's changing at the same magnitude in negative and in the positive, they will always cancel out. There will not be any sort of absorption. And that is very important because you will not always see all of the absorptions or all of the vibrations or all of the bendings of all the molecules, only the ones that are IR active. That is the point of all this. Okay. And then if you really, really want to know the physics, this is the formula. This just drives the point home even further. You have this wave number formula. You have 1 divided by 2 pi c. I'm sure c is some sort of constant. F is the force constant. In other words, how strong is the spring? And then the reduced mass is just the center of mass of that spring. This is physics, and we are in OChem, so I don't want to get stuck too much into this. But if you really want to prove that what I told you is true, which is, stronger bond requires more energy. This is the equation behind that rationale. So you can try it, you can plug in numbers, it's up to you. I don't really want to focus too much on it. What I do want to focus on is, once again, if you look at the blue, it says that the strength of the bond is also what determines where it is in the spectra. So single bonds are weaker than double bonds, so they're going to be at a lower wave number. Double bonds are stronger, so they're going to be at a higher wave number. And triple bonds are even stronger than double bonds or single bonds. So triple bonds are usually in the high wave number areas. And similarly, polar bonds or bonds of atoms with different masses are also going to be in higher energy areas compared to the other ones. And so we'll see that again once we start actually identifying it. So the intensity depends on polarity. It depends on intensity of vibration. It depends on differences in mass. It depends on the energy of the incoming photon. Lots of factors that go into it. But this is physics. You can take more physics if you would like to really get into the mathematics and, reasonings behind it. Us organic chemists simply want to know, cool, that's nice. Now, can we actually see the molecules? Can you actually show us the fingerprint? Yes. So here it is. This is what a real life infrared spectra actually looks like. And so again, look at the y-axis. Percent transmittance. What percent of the infrared photon went through the molecule? 100%? No absorption. 0%? Complete absorption. But it's never one or the other. It's always somewhere in between. So the intensity of the transmittance or the intensity of the absorption is one of the clues about what sort of functional group you have. The shape, you can see the shape of some of these peaks. Some of them look really sharp, like the stalactites of a cave, right? Very sharp peaks at the top of the cave or at the bottom of the cave. Some of them are more broad. They look more like a blunt, like pencil, like for example, if you look at 3500 wave number, you see you have we call that a broad peak. And it has a high intensity, so we say strong, broad peak. And then this peak over here at 1500, you see that it has like a medium type of intensity. Like it's a little more than 50, but I mean, less than 75, I would say. So I would still call that kind of medium or slightly strong, but I think medium is the proper term. And you see the peak is sharp. That is a very pointy peak. So we call that a medium sharp peak. That is how we describe it. And so we have also the intensity, the shape, and the wave number. Remember, the wave number tells us what energy the photon had. Higher wave number, higher energy. I think it's very straightforward. Lower wave number, lower energy. More polar bonds and smaller bonds and triple bonds will vibrate at higher energy. So you are going to find those signatures over here in the 4000s, 3000s, 2000s. Single bonds are going to vibrate at lower energy. So you're going to find that in the 1500s, the 1000s, and the 400s. The region between 1000 and 400, we generally ignore because we call that the fingerprint region. I know I tell you that these spectra are fingerprints, but we're looking at specific parts of the fingerprint. These peaks are kind of there. They could be caused by anything, really. Like the thing is that if the slightest amount of energy causes a vibration, that could be caused by the photon, that could be caused by ambient heat, that could be caused by the collisions between the molecules. There's no real way to point out which ones of these fingerprint regions were caused directly by the photon because almost any other sort of motion or thermal motion has very similar energy. So we want to focus more on the higher energies of the photon. That is why we mostly look after 1500. And that is also why the scale is organized in this manner. You see that the higher numbers are a little bit more compressed. The lower numbers, they still give us some information. So we're going to see, we're going to be looking a lot at between 1500 and 2000. But in general, anything below 1000, we kind of don't really pay too much attention to. Does that make sense? So again, three important characteristics. The wave number. In other words, what energy is that molecule vibrating at? The shape. Is it sharp? Is it broad? That tells us a lot. And the intensity. What percent of the photon's energy got absorbed? Only 20% or a lot? That tells us about polarity and other sorts of things. So these are the things that we're going to be thinking about when we are looking at the actual spectra. So we look at the four regions. I just told you guys anything between 1000 and less. This chart says 1400. We call that the fingerprint region. Again, that's where the single bonds are at. Double bonds are going to be here between 1600 and 1800. And then the triple bonds are going to be over here between 2000 and 2500. And then we have these bonds here, nitrogen, hydrogen, oxygen, hydrogen, carbon, hydrogen. Those are polar bonds, but more specifically, nitrogen, hydrogen, and oxygen, hydrogen can create hydrogen bonding, which is an additional constraint. You can think of a hydrogen bond as a secondary type of bond. So not only do you have a covalent nitrogen-hydrogen bond, now you have a hydrogen bond to another nitrogen-hydrogen bond of another molecule. That pseudo bond increases the stiffness of the spring. So you need even more energy to vibrate those bonds right there. That is why you see nitrogen hydrogens, oxygen hydrogens, fluorine hydrogens are going to be in the 3000s, 3500 regions. As far as I know, I don't think anything actually makes it to 4000. I don't think I've ever seen anything like that, but I'm sure something exists out there. But this is good to have in your head. This is good to have in your head. You don't have to memorize all sorts of specific bonds. Look at the trend, right? In the orange, the single bonds are low energy. Then you get the double bonds, then you get the triple bonds, right? 1, 2, 3. 3 is bigger than 1. 3 has higher energy. I think it's a very easy way to understand it. The nitrogens, oxygens, and fluorines and CH, remember CH is a polar bond. It doesn't hydrogen bond as strongly, but it's barely there. It still contributes in terms of IR. So those bonds, even though they are single bonds, they create hydrogen bonds and they are also polar bonds. So those bonds are going to be the highest energy. That is why we get this distribution of the IR spectra. So are we okay with this? Like thumbs up so far? Like we're about to start talking about specific functional groups. So before I do that, I want to make sure that we're clear on this. Just give me thumbs up or say yes or any questions. This is a good time to ask. Okay, sounds good. Alrighty. Thank you guys. Thank you. Appreciate it. Okay, so here we go. We're going to start with the most basic type of molecule and the most basic type of bond, the alkane, alkene, and alkyne. If you have not yet learned your IR, I'm sorry, not your IR, your organic nomenclature, you need to do that because we're going to start speaking organic chemistry. So alkane, alkene, alkyne, that simply means only hydrogen, only carbon. In other words, only hydrocarbons. And remember, carbon can make different types of hybrid bonds. Remember, we're looking at the vibration of the bond, so we have to look at the hybridization of that bond. So depending on the type of character it has, if it's completely a p orbital or an s orbital, or it has a bond with something else like an sp, sp2, sp3, that is going to give you a different energy. And so in order to help you with that, sp, triple bonds. Triple bonds are smaller, stiffer springs. So sp is going to be high wave number. sp2 is lower wave number. sp3, in other words, single bonds, are the lowest. And of course, p would be even lower than that. We wouldn't even perceive p. And then S, well, S would be the highest, so but that would just be a naked carbon atom by itself. So again, sp2, sp3, in other words, triple bonds, double bonds, or single bonds, that also correlates to where exactly you're going to find these things. And it is the hybridization that causes the shift in the wave number. So you see over here on the very left bottom, we have this carbon hydrogen bond, sp3. You see it vibrates at 2900 wave numbers. 2900 wave numbers. You can't really see the peak. It's in there in that it's right over here. You can see the blue arrow is pointing to it. It kind of blends in. Right off the bat, this is the first lesson. This is the first thing you need to learn. Everything that is usually between 3000 and 2800, those things are always going to be some sort of carbon hydrogen peak. So that region, this little stalagmite you see right here, that is always going to be there. Because think about it, organic compounds are made of carbon, and hydrogen and carbon atoms, bonds are everywhere. So you're always going to see some variation of these alkyne peaks in all of your spectra. So you need to learn when to notice it and when to ignore it. And also, I want to also point out, it is impossible to be given a spectra and to be asked, tell me what molecule that is. I'm sorry, I cannot do that. I need to know how many carbons I have. I need to know how many hydrogens I have. I need to know what sort of other atoms are there, right? Because what if they're not IR active? The IR spectra is one of the many pieces of the puzzle that we use to identify our molecule. And since we are using organic molecules, everything has carbon hydrogens. So everything is going to have this. Sometimes we don't care about it because of course, carbon hydrogen is there. I know that. It's an organic molecule. So it's there. Make sure you don't use this and confuse it for something else. Whenever you see this stalactite formation from 2800 to 3000, it's always one form of alkane, alkene, or alkyne. If it's an alkane, it'll usually be at 2900, maybe 3000 itself. If it's an alkene, remember the alkene is a smaller spring, so it's going to vibrate at a higher energy. And sure enough, you see right here that the alkene peak, it's very weak and sharp, not a lot of transmittance. This vibrates at 3100, higher wave number, higher energy, because it's a stiffer spring, it's a smaller bond. The alkyne, the triple bond, is the smallest and the strongest of the carbon-hydrogen bonds, carbon-carbon bonds. And so you see the peak, it's a very weak but sharp peak at 3300. So you see that as your hybridization goes from sp3 to sp, you have a higher wave number. So these peaks tell you if you have an alkane, an alkene, or an alkyne. But notice in all three cases, you get that weird stalactite formation right there at 3000. So you got to know when to look at it and when to ignore it. Does that make sense? Are we okay with this so far? So this is our first functional group. First skill of the day. If you see the stalactite at 3000, 2800, that means CH something. Maybe not exactly all the information that we need. Okay, so the next group, oh, this is an example. Octane. Again, you have that little stalactite here, CH3, CH2. No functional groups. You don't have any carbon oxygens. You don't have any carboxylic acids. You don't have any amines. So all you see is a relatively peaceful spectra. There's not a lot going on. And the only peaks you're really going to see are very basic CH peaks. So you see here, remember, bending is always lower energy than stretching. CH3 bending, CH2 bending, those are going to be a little bit lower energy. And then the stretching are always going to be at higher energy. But otherwise, you don't see anything at 1600. You don't see anything at 2000. You don't see anything at 3600. Like this is strictly just a boring old alkane. No offense to octane, you know, we use it in our gas every day, but in terms of IR, it's not very exciting. So sorry, octane. That is why we use you for synthesis. Okay. Aromatic compounds are also considered CH compounds, but the difference here is you have the introduction of that double bond, but also you have what the resonance effect. Remember, the double bond can delocalize and be spread around. So benzene doesn't actually have single bonds and double bonds. The whole ring the bonds of that whole ring are all the same size, and it's more of a 1.5 bond, 1.5 bond. So it's not going to be as strong as a double bond, but it is going to be a little bit stronger than a single bond. So it's going to be somewhere in between. And you see here in this example of toluene paint thinner, you can buy this at Home Depot. You see you have this aromatic carbon-carbon double bond stretch happening at around 1500. It is a medium sharp peak. There's also a weak sharp peak next to it. We don't know what that is. Sometimes we don't know what the peaks are. Sometimes we have to guess what they are. We can't just throw out words though. We can't just say like this is a carbon hydrogen hula twist. No, we can't say that. If we don't know, we just flat out don't know. Okay, we have to compare it to another known spectra or another known journal that already took time to actually figure out what's what. But sometimes we just don't know. And once again, I want to draw your attention to around 3000. You have another type of stalagmite formation, those pointy things at the top of the cave. Notice this time it's not very intense. Why is it not that intense? Because remember, double bonds are stiffer. Remember I showed you in that drawing, the little animation, it was wiggling, but it was a lot more stiff when it was wiggling. So therefore, the intensity is not as strong. And that's why you have that formation, but instead of it being so intense that it almost absorbs almost everything, this time it's only at, for example, at most 70% absorbance. Does that make sense? So remember, double bonds are smaller and stronger. 1.5 bonds are not as strong, but still stronger than single bonds. So the smaller the bond, the stronger the bond, the more polar the bond, the higher the energy, and the higher the intensity that is necessary to absorb that energy. And then here, they actually make a use of the fingerprint region. Of course, it's a CH bend. What else is there? There's nothing else. There's just carbons and hydrogen. So, of course, we can use the fingerprint region in this example because we can kind of see what it is. Again, you will always know kind of what you're looking for in an IR spectra. You don't just go in blind. I am not going to give you a spectra and tell you, draw the whole molecule. I have to give you options. For example, hey, here's some options of what molecules they could be. Based on what you know about spectra, tell me which one is most likely corresponds to which one. But I'm not going to give you just a spectra, no examples, no molecules, and tell you, draw the molecule and make sure you get it exactly correct. That's not possible. You need more information. You at least need to know what you're expecting. So that is why we can assign peaks. So this is the case for aromatic compounds. We have the aromatic CC stretching between 1400 and 1600. And then, of course, we have the AR. AR means aromatic or aryl. Means the same thing. That is a stretch for simply those bonds inside the ring, just kind of like stretching. Does this make sense? Are we okay with this one? Any questions so far? Ask me questions. Okay. Okay. So other functional groups. This is the main one. This is like one of the main characters of IR right here. The carbonyl. Remember, carbonyl means carbon, oxygen, double bond. Carbon, oxygen, double bond, carbonyl. When I say carbonyl, I mean only carbon, oxygen, double bond. Make sure you don't confuse it with carboxylic acid. That is carbon, oxygen, double bond, OH. Make sure you don't confuse it with anything else. It's when I say the word carbonyl, I'm strictly talking about carbon, oxygen, double bond only. Is that clear? Carbon, oxygen, double bond only. That means carbonyl. This is a very specific bond. It is polar. There's carbon and oxygen. It is a double bond, so it's very strong. And then it always absorbs in a very narrow range, narrow enough that it's characteristic, and it is always strong absorption, meaning a very strong peak. So the next thing you guys are going to learn is every time you see a spectra, I would recommend the first thing to look out for is find the carbonyl. Either it's going to be there or it's not going to be there. If you find a carbonyl, now you know you have one of these functional groups down here. So you can have an aldehyde, you can have a ketone, you can have an ester, you can have a carboxylic acid, amide. All of these contain a carbon-oxygen double bond. In other words, all of these contain a carbonyl. And depending on the substituents, depending on the number of oxygens, depending on the polarity, depending on its environment, you can find these specific carbonyls in very specific regions. Some carbonyls are stronger than others. All carbonyls are equal, but some are more equal than others. And this is the case. You see that the amide carbonyl is the weakest of them all because of that nitrogen. It's not as polar as oxygen. So, oxygen is stronger than nitrogen in terms of electronegativity. So oxygen is going to create more polarity. Therefore, oxygens are going to be higher energy. So you can see the amide carbonyl is going to be the weakest, followed by the carboxylic acid at 1700 to 1780. The ester is somewhere in between. There's two oxygens there, but that oxygen is connected to another carbon. So not as strong as the carboxylic acid, but they do kind of overlap. So in this case, you will have to look for other peaks besides just these, but you know at least that the carbonyl is present. A ketone is just a carbonyl with carbons around it, no other oxygens. That one can vary depending on what that is. Like if it's connected straight to an aromatic ring, it's going to have conjugation, which is going to weaken the bond, which is going to bring it to the lower end. If it's connected to simply just a non-aromatic or what we call aliphatic, only carbon hydrogen single bond chain, that is going to be at a little bit of a higher energy. And then you can see the aldehyde also is kind of all over the place. Depends on what that R group over here is. If it introduces conjugation, it's going to weaken the bond, and that is going to be in the 1600 region, 1690, like low 1700s. If this is just another chain of other carbons, that is going to be at a higher energy. If this R group is like a chlorine, that is also going to be way higher energy. And sure enough, you can see them here. It says 1800 acid chloride. And then anhydrates, well, that's just another type of functional groups. That is carbonyl, oxygen, carbonyl, oxygen. There's like a very concentrated oxygen center, but you guys can look up what that looks like. I don't think that this slide provides it because we don't really deal with anhydrides. We mostly deal with these functional groups right here. And I want to emphasize, this is very important. This is a guideline. This is not absolute. Just because it says ketone 1715 does not mean there is always a ketone at 1715. But it's around there. It's around there. This is like a relative scale, right? Carboxylic acids will be there, ketones will be a little bit to the right, but not always, right? So don't take these values to 100% hard. Take it to like 70% hard, right? Know where to look. So when I show you spectra, I'm going to tell you guys, look at 1700. Look at the 1700s. Do you see the carbonyl peak? And then it's either going to be there or it's not. And then only with other information can we determine what sort of carbonyl, whether it's a carboxylic acid or an ester or an aldehyde, blah, blah, blah. But what I want you to take away from this slide is that the carbonyls rule the 1700s. Carbonyl will always be somewhere in the 1700s. Very strong peak, very iconic, very characteristic. You can't miss it. Highly identifiable. So I think there's some example slides here coming up. Yep. So for example, here's the first one, butyraldehyde. You see the structure is right over here. Oh, sorry, bottom right. Butyraldehyde, you can see bottom right. And then on the top one, you have 2-heptanone right there. Both of these compounds contain carbonyls. One is just a ketone carbonyl. One is an aldehyde carbonyl. So let's take a look at the first one, 2-heptanone. You see that CO peak at 1718. Look at the shape. I want you guys to take a second and look at that shape. That is what most carbonyls are going to look like. So when you see that peak at 1700, that looks like that. 90% of the time, that's a carbonyl peak. I almost remember that Leonardo DiCaprio meme where he's pointing at the screen. It's like, you see that peak and it's like, carbonyl, carbonyl. Like, that's the carbonyl peak right there. Look again at 3000. What do you see? You see the stalagmites. Those are always going to be there. There's always going to be some variation of the stalactites at 3000 because these are organic compounds and everything has CH somewhere in some form. So those are always going to be there. You need to know when to pay attention to them and when not to. And it is actually quite frequent that we take an infrared spectra to identify a single functional group. Sometimes we just want to know, like maybe we started with a regular chain, we started with an alcohol, and we want to know if we can convert it to a ketone. That is possible, by the way. You can convert an alcohol to a ketone. And so you would see in your starting material, the alcohol, you would not have that CO peak. And then if your synthesis was successful, you will create that carbonyl. And then you will see when you take the spectra of your product, that CO is there. That is confirmation that your synthesis was correct. So this is an example of how we use IR to identify compounds. Oh, sorry about that. At the bottom one, this is an aldehyde carbonyl. Notice that the peak is a little bit broader than simply a ketone carbonyl. So that's one of the characteristics. It's around the same region, right? This one's at 1720, the one is at 1718. So this is what I was trying to tell you guys. You can't take the numbers to heart. These guys don't really care about numbers. It's our instruments that are assigning those numbers. So just know that it's in that region and then look for other clues. In this example, you see that the stalagmite pattern has changed because now you have a carbon hydrogen, that terminal aldehyde carbon hydrogen bond right here that is being impacted by the polarity of that carbon oxygen double bond. This carbon oxygen bond is polar, so it also makes this carbon right here a lot more positive, which draws the electrons from this hydrogen more towards it. That is going to change the strength of this very specific carbon hydrogen bond, and it is going to appear as slightly lower peaks than the stalagmites at 3000. So you see there's a peak at 2720 and there's a peak at 2820. This is like shooting arrows, the darts into the dark. But they do kind of nail it because we don't know which of the two peaks are specific to which motion, but we know that because we expect an aldehyde and we have that carbonyl, that must be it. Which one exactly? I can't tell you. I just know that it's one of those two, or possibly those two. And you see also in the fingerprint region, you have kind of like a stronger something peak at 800. That could very well mean something too. You also have this peak at around 1400 in the bottom spectra. That could be a carbon oxygen like something, but we don't really care. The only thing we're looking for in these specific spectra is the characteristic iconic, the main character carbonyl stretch in the 1700s. So now you know that if you see the stalagmites, you have your carbon hydrogen stretches. Now you know that if you see this specific peak at 1700s, you have a carbonyl. You need to remember this. All right, are we okay with the carbonyl peak? Okay, cool. All righty. And again, we keep talking about conjugation. Again, conjugation means alternating single and double bonds. So benzene rings, aromatic compounds, and sometimes just an incidental alternating single double bond. It delocalizes the bonds. It weakens the bond. And since the bond gets weaker, it takes less energy, so it lowers the wave number. So talk your way through all that, okay? Stronger bonds, stronger energy, weaker bonds, weaker energy. Conjugation weakens the bond, so conjugation lowers the wave number. And it says here that it can lower the wave number by around 30 or so. So if you have a ketone, for example, at 1720, a conjugated ketone will have a weaker carbon-oxygen bond, and that is going to cause it to shift towards the 1600s. It's still close enough to the 1700s that you can identify it, but it's not going to be exactly in the 1700s. And this is another example how you can have a carbonyl, but depending on what is around it, that also affects the wave number. It's not simply the carbonyl by itself. The molecule is a complete system. We're trying to look at small parts of the system, but it's still a complete system. You can't look at one and not consider the rest of the molecule either. That makes sense? So the conjugation effects will always weaken the wave number. Okay, alcohols and phenols. This is another characteristic, main character, you can't miss it type of signal. If you look at this example, 1-hexanol, you see this very broad. I want to emphasize that. Look, if I look down here, that's at around almost 3000, right? It starts at 3000 and it goes really broad in intensity. It increases in intensity until around 25% at around 3400. And then the peak continues all the way until it goes back to lower transmittance at around 3700. So this goes from 3000 to 3700. That is a range of 700 wave numbers. That is broad. That is a very broad peak. Remember, carbonyls stick within the 1700s. That's only a range of 100 wave numbers. The the alcohol peak is going to be very broad. It's going to stretch anywhere from 700 wave numbers to 1,000, depending on what type of alcohol it is. So when you see this broad, strong peak, very commonly to the left of the stalagmites of the CH stretching, that is going to very likely, almost 95% of the time, be some alcohol. And that is what it looks like right here. 1-hexanol, you can see you have this very broad alcohol stretch. And that is also what the slide says as well. Also, you have that hydrogen bonding. So I guess concentration does matter. You can sharpen the peak by making it more dilute. But most of the time, you just want to know if the alcohol is there. And either way, both of the peaks, both of the wave numbers, whether it's dilute or whether it's concentrated, are relatively iconic and easily distinguishable. So it doesn't really matter much. But again, you know, when you have hydrogen bonds, you create a stronger bond, and also you're pulling the bond apart. So you kind of increase the energy required to vibrate it while simultaneously doing a decreasing strength of the bond. That is why you have a very broadening of the signal. There's too many things you're trying to vibrate at the same time throughout a different range of wavelengths. That's what causes the broadening. And then also you see they take the time to point out at around 1100, you see there's a very, I would call that medium sharp carbon oxygen stretch from that alcohol. This carbon here is bonded to this oxygen, which is bonded to this hydrogen. That also vibrates. That is also a polar bond, but it's a single bond. It's not a carbonyl, so it's always going to be lower than 1700. And it's too close to the fingerprint region. So unless we really like need more info, or unless we really want to be like, well, you know, by the way, there's this. It is cool to know, but it's not necessarily super important. If I was looking at the spectra, this OH right here is what would tell me, yeah, this is an alcohol of some sort. So does this make sense? Are we okay with the alcohol so far? Hopefully you're not drinking alcohol right now, but just because it's too early, you know? Well, let's talk about a very specific type of alcohol, carboxylic acids. Remember, if it's just carbon, oxygen, hydrogen, that's called hydroxyl or alcohol. If it is carbonyl and then alcohol, carbonyl and then alcohol, C double bond O OH or COOH, that is its own unique functional group. It is composed of two, but it is its own unique functional group. It's called a carboxylic acid, not a carbonylic acid, not a carbonyl acid, carboxylic acid. You need to have that X in there, X and the Y. That's how you remember it. Carboxylic acid. If you don't have that hydrogen at the end, it's called a carboxylate, but it is a carboxylic acid. And since you have two types of bonds in this compound functional group, you are going to see the spectra starting to get a little bit more complicated. A carboxylic acid contains a carbonyl and it contains an OH. So you are going to see both of these signals. So once again, direct your attention to 1700. There is your very iconic carbonyl peak right there. Strong and exactly at 1700 or so, just as expected. So that's how we know this is a carbonyl. And then take a look at the OH. Remember, alcohols produce a very strong, broad signal. This is definitely a broad signal. Look, it starts right here at around 2300. It starts here and it goes all the way to around 3500. That's a range of almost 1,000. I think it's 1200. I don't know exactly, but it's very large range of wave numbers. It actually overlaps with the stalagmites of the CH3s. You see, you have the stalagmites at a slightly higher intensity. They have been overlapped with the OH broad signal. So this produces another characteristic and iconic signal. Carboxylic acids have this broad signal. The organic chemists call it the beard. So this is the beard right here. It's almost like the wizard's beard. I don't claim to have one, but this is the beard. This is how I remember and how I identify specifically a carboxylic acid versus an alcohol. If we look at the previous slide, you see the alcohol doesn't have the little spiky things at the bottom. You see the alcohol broad signal is more to the left of the CH3 stalagmites. But over here in carboxylic acids, they will always, well, not always, like 90% of the time overlap. And that gives like a little scruffy wizard's beard kind of look. And so that is why I'm saying if you see the beard and you see the carbonyl, almost 100% of the time at that point, like that's how iconic this is. Almost 100% of the time, that is definitely a carboxylic acid. So this is what a carboxylic acid looks like. And again, sometimes we look at an IR for just one single functional group. So even though there's some stuff going on at 1000 and 1500, and sure, you could be like, well, that peak at 1200 is probably a carbon oxygen stretch. Yeah, probably, cool, but I see the beard. I know it's a carboxylic acid. I don't let me know if I ask, kind of like that. So again, this is what a carboxylic acid looks like. Are we okay with the beard? Are we okay with the carboxylic acid? Like any questions so far? Okay. Alrighty. Um, ethers. Ethers are carbon, oxygen, carbon single bonds. So it's carbon, oxygen, carbon. Carbon, oxygen, carbon. If you're a fan of Fear and Loathing in Las Vegas, they talk about diethyl ether. It was one of the first anesthetics ever used in the United States. Before that, if you ever had surgery, you basically just had to deal with it because they didn't have very good anesthetics. They would basically use ice to numb you down, or they would try to sting you with like the ants so that the poison would be more painful than the surgery, or you basically just died from pain and shock. Diethyl ether was used as the first anesthetic. They put it in the rag. They put it over the guy's face, and then they cut into him, and he did not scream in pain. And they were like, "Holy Lord, we have changed surgery forever." So that is the most famous ether. It is a dissociative. Do not huff it. It kills brain cells. Not a good idea. But if you do want to know if you have an ether, this is how you do it. You basically have a single type of polar bond. You have a carbon oxygen single bond, polar, so it'll stretch, and so you can find that signal of that stretch. So this is dibutyl ether, meaning four carbon chains, oxygen, four carbon chain. That is dibutyl. Butane has four carbons. Ether means there's an oxygen linking the two. So four carbon chain, oxygen, four carbon chain, dibutyl ether. Well, look at 3000. What do you see? The iconic stalactites, the CH3 stretches are already there. That's cool. Of course, we have that. It's an organic molecule. But what I'm looking for is that CO stretch because I know I have an ether. Well, it looks like a carbonyl stretch because it's a polar bond, but since it's a single bond and it is not a double bond, that CO stretch is usually found between 1000 and 1200. Maybe 1100 is a good reference point. And sometimes their intensity varies. So it's not as iconic. It's not really something that we kind of look for unless we suspect we have an ether or we have an ester. But you still need to know basically where to look for it. And you can see right here the formula for that butyl ether. There's also these two peaks up here. That is probably some sort of other carbon oxygen stretch happening somehow, somewhere. We don't really know. And frankly, whoever did this spectra did not consider it important enough to try to determine what it was. You don't go into these spectra blind. You at least have some sort of idea of what kind of things you're looking for. So it is just still worth talking about ethers and more specifically carbon oxygen single bonds. So are we okay with this? Okay. So again, sometimes you have esters which contain both carbonyls and carbon oxygen single bonds. Those produce both signals. So again, this is ethyl butyrate. You can see right over here is the structure. You have your typical carbonyl. So there it is. Go to 1700. Yep, there it is. There's my CO carbonyl stretch happening at 1700, just as expected. And I just told you guys about the carbon oxygen single bond stretch between 1000 and 1200. And it's also relatively strong intensity. So you see right there, the sharpest of them all. Well, not the sharpest, I'm sorry. The most intense of them all in between 1000 and 1200 is the carbon oxygen single bond. And then I guess they felt the need to point out that this one was also some sort of a stretch, but I mean, that's kind of a stretch, right? Like it could also be any one of these other ones right over here. So I'm not sure. I will debate the one at 1000, but definitely 1200, you're like spot on. You bet that is a carbon oxygen stretch. Um, Give me a second. I think I unplugged my screen. See, this is why I would prefer to do things in person. Hold on, quick second. Sorry about that, guys. Okay, I can see you all again. Awesome. Cool. Alrighty then. So we're back. So we were talking about esters. We have carbon oxygen stretch, we have carbon oxygen single bond stretch, and then once again, if you look at 3000, you will see the stereotypical stalactites present right there as well. If you look at the bottom spectra, you have methyl benzoate, and that has a little bit more of a complicated signal because this signal is conjugated. That carbonyl is now conjugated, and that conjugation is going to change some wave numbers and is going to introduce a lot more signals and a lot more things. So if you look, for example, over here at where is it? At 1700, you have your stereotypical carbonyl peak. You have your aromatic carbon-carbon stretches happening in between 400 and 1600. You also have your carbon-oxygen single peak stretches. And then, of course, if you look at your stalactites, you will see that their intensity has lowered because now that it is conjugated and it's also double bonded, now you have more strength of the bonds. Therefore, it is not going to be as intense. So does this make sense? Are we okay with this so far? Thumbs up. We good? Yep. Alrighty, sounds good. So moving on to the next thing. This is our next group, the amines. This is another very characteristic, iconic, you can't miss it type of signal. Amines are nitrogen-hydrogen bonds. Nitrogen-hydrogen bonds. And you have two types. You have either primary amines, which means that you have a single carbon-nitrogen bond. Primary meaning single, primero, right? Carbon-nitrogen bond. If you only have one of them, it's primary. If you have two of them, they are secondary. So you have primary amines and secondary amines. And primary amines are going to give you two signals. Those signals are the nitrogen-hydrogen stretches. Nitrogen-hydrogen stretches. Since you only have one bond here, since you only have one bond there, that is going to give you a stretch somewhere else, but you have two nitrogen-hydrogen stretches, therefore you have two peaks. If you only have a single nitrogen-hydrogen stretch, you will only have one peak, and therefore you can actually see which of these you have based on the number of signals that are present there, which I think is pretty cool actually. And of course, if you have a tertiary amine, that means you have a nitrogen with three carbon bonds. No nitrogen-hydrogen stretches, there is nothing there. Does that make sense? Like, we okay with that? I think my mouse also disconnected, I just noticed. So I'm gonna be using my little stylus here, but I'm not sure if it's gonna be a good idea. So let's see if it works. Alrighty. Are we okay with the means? Do the means make sense? Basically, you just look at between 3,200 and 3,500, and you look at the number of peaks. That tells you, first of all, there's an amine, and it also tells you what type of amine it is. You know what I mean? Okay. So here we go. Now we actually get to test our knowledge, see if we actually learned anything at all, or if we just dozed off for the past hour or so on Zoom. So this is for you guys. What functional groups are present? What do you see here? I guess this would be a good time for me to try to fix my mouse because I do need to be clicking on things. Give me a quick second. I'm going to turn off my video. I think this would be a good time to pause the recording. Let's see. How do I do that? I'm going to pause the recording. All right. Recording in progress once again. We continue. Okay, so I was taking a look at the chat right now, and most of you guys already found the answer, which was definitely a carboxylic acid. And how can you tell it's a carboxylic acid? The beard, that's right. The beard, the wizard Gandalf beard, exactly. Very iconic. You see that you have the stalactites at 3,000, and then you also have the very broad peak that starts from 2,500 all the way to 3,500. And then, of course, who can forget the carbonyl that is present right there at 1,700? So carbonyl plus beard gives you carboxylic acid. Very straightforward, I think. Remember at the beginning of the presentation, I told you guys you were going to be looking at this graph and you were going to be like squiggly lines. But now you're looking at this graph and you're like, oh my God, that's definitely carboxylic acid. Holy Lord. So now you know that when you see this, it actually means something. So here's the next one. What is this?
Dr. Vite, I have a question.
Yes,
For the last one, if you just put, for example, just like carbonyl acid, do you get like at least like half points off? Like,
that's not the proper term. It's a carboxylic acid. So even though I would know what you mean, you're still incorrect.
okay, okay.
You have to say what it actually is, right? Carboxylic acid. Like I'm sure everybody wants to be called by their actual name, right? So you gotta call it what it is. It's a carboxylic acid. It does contain a carbonyl, you're right, but Its name is carboxylic acid.
Okay.
Mhm.
All
So
right,
you
thank
have to
you.
say, yeah, yeah, thank you. Yeah. Any other questions? Yep. So make sure that we do that too, because I did observe that also in some quizzes. Some people were saying things like that. You have to call things by their proper names. Carboxylic acid. So what about this one? What is this one here? What do you see? What functional group? Okay. We got a good answer already. What do you guys see? Are you saying OH or are you saying O? I can't tell. Oh. Hydroxyl, there you go. Yeah, good. I see an OH. Yeah. You could say an OH or yeah. And then Tony definitely said O because he lowercased everything. Yeah. If you're gonna say OH, at least I know you're saying OH if you have capitalized it. So make sure that you either make you can say alcohol, you can say hydroxyl, or you could say an OH. And then I know you're talking about the OH itself. So you definitely see the alcohol signal kind of medium at around 3,500-ish, a little bit less than that. That is definitely an alcohol. And then is there a CO? There probably is a CO actually. Which one do you think would be a CO? Because if there is a COO, if there is a COH, there's also a CO, right? 1,500? Possibly. I mean, it is a slightly polar bond, but not as polar because of that hydrogen. I would say, yeah, it could be any one of these peaks. It could probably be the peak at like 1490. It could be that peak at 1500. I don't think it's that peak below 1000. That's definitely something else. But I mean, it could be one of these three peaks right here. But this is also kind of what I mean, right? Like if we see the alcohol, we kind of already know through deduction that there is also a carbon oxygen bond. So, I mean, it's not really a priority to try to point that out. And what else do we see? What do we see that is present in every single slide so far? See, you guys didn't even notice it. You guys just ignored it already. Exactly. That CH stalactite stretch is already there, but we know it, so we kind of are like, yeah, cool. Hey, good to see you again. But who's that? That's the alcohol right there. So, alrighty, cool. So you guys are getting good at this. So what about this one here? What do we see? All right. Uh-huh. Uh-huh. Definitely, definitely correct. Yep, for sure. This is definitely an amine, right? NH is a very polar bond. It also participates in hydrogen bonding, so it broadens the signal. And so, and it is above 3,000. Yeah, exactly. So that's how you know that it is an amine. And then you have to be more specific because remember, when we're doing IR, we can actually see what type of amine it is. So you guys said amine, make sure you tell me what type. Is it primary? Is it secondary? And I already saw a few people say primary. How do you know it's primary?
Is it because of the specific shape it has?
The specific shape is one aspect of it. What about its shape? What is the shape like?
It has two peaks? Or
Exactly. Exactly. Twin peaks. Yeah, exactly. It has the two peaks. Yeah, exactly. The two peaks of the amine correspond to the NH peaks. And let me see. I was trying to draw earlier with the tablet. Let me see. And oh, awesome. I can draw. Can you guys see the drawing? Cool. I didn't know I could do that. So yeah, since it has two NH stretches, these NH stretches are these right here. That's this right here. It's primary because it has a single bond to a carbon. So this is a primary amine right there. Or Twin Peaks, if you want to call it like the place. And then also notice you have the stalactites. And I'm sure that that peak at 1500, that's probably a carbon nitrogen stretch of some sort. But, we already know that it's there because an amine, a primary amine, has a carbon nitrogen bond. So that's kind of information we deduce. We can't point it out. We can say, This peak right here is probably my carbon nitrogen stretch. Wow, I wish I knew I had this pen. Alrighty. So any questions about this specific spectra here? Okay, so what about this one? Secondary amine. Okay. Any agreements or disagreements here? Okay, secondary amine, one peak. Okay, good. Anyone else? Agree, disagree, or not sure what's happening? Okay. Yep. So this is definitely a secondary amine. Secondary means you have two nitrogen carbon bonds and you have only one nitrogen hydrogen bond. This NH is what that peak is right there. It is a polar bond, so it is broad. You see that the signal is a little broadened right here. It looks like a peninsula of sorts. And then, of course, it's always going to be higher than your CH3 stalagmites right over here. So this is definitely an amine peak. And since you have two carbon nitrogen bonds, I almost want to say that either this peak here or this peak here is probably a carbon nitrogen bend of some sort, or maybe even a stretch, but I can't really say definitively, right? Again, this is kind of more like, well, I see some peaks and, based on what I know about IR, it's very likely this is what it is, but I say that because I believe this CN bond will behave very similar to a CO bond. Oxygen and nitrogen are right next to each other on the periodic table. So there's that right there. So does this make sense? Basically, primary amine. Okay. So what about this one here? What is this? What do we see here? Okay, we got one answer already. Yes. Yep. 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 Exactly. That is an alcohol. And where is it at? We also see that CH3 stretch. Yep. Correct as well. So yep. So again, you guys are getting good. You see right here your OH stretch. And usually when we report peaks or when we talk about peaks, we talk about like the place where there's strongest intensity. I know it's not a straight line right there, but that's probably like around 32, 32, 50, 33 right there. And then you have your CH stretches. And then right here, this peak right here, I'm pretty sure that is also your carbon oxygen stretch right there. Either that one or this one of those two. Again, if you have an alcohol, you know there is a carbon oxygen bond. So, I mean, it's not particularly necessary to know. The important part is you recognize this is a strong, broad peak right here. See, very broad, covers a lot of wave numbers. CH stretches, they're always there. Good to see you again. But yeah, this is definitely an alcohol or hydroxyl group. What about this one? Panic. What do you mean panic? There's hardly anything here. Unless this is your heart monitor when you're panicking, then yeah, maybe. So what do we see here? All right, so definitely CH structure. Yes, exactly. The question was, does this count as a CO double bond? Well, there is not a very strong peak at 1700, so there is no carbonyl here. This has a notable absence of the carbonyl. I'll let him know that you miss him though. It said a CH stretch. Yes, of course. At 3000, you always have your CH stretches. Tony says CH structures. Exactly. Yes, yes. Not really any strong peaks. Exactly, exactly. There's also not really much else happening, right? So remember, The alkane, alkene, alkyne spectra are relatively boring. There's not really much to look out for. There is a little hidden detail here, though. I'll give you a clue. What's happening here and what's happening here? What are those? Well, amines have more of a rounder peak. This is a very sharp peak. And remember, we just agreed that there's not really much happening here. So this is some sort of hydrocarbon only. This is a sort of hydrocarbon. There's no amines, there's no carbonyls, there's no carboxylic acids. There is something though. What are those two peaks that I drew at? You guys got comfortable with the iconic ones. The true skills come from seeing the subtle details. Come on, I need some guesses. I need some guesses here. I can't just have Tony guessing everything. What are those two peaks? You're gonna see something like this on the final exam. You gotta make some guesses. Nobody? Ferris? Ferris Bueller? Anyone? Alrighty. Well, we're still learning, so no shame, no shame. Remember the very first group that we learned that whether you are sp3 or sp2 or sp, the wave number will increase. So sp is going to have a peak at a higher wave number than the typical stalactites, sp2 a little lower, and sp3 is just going to blend in. So this right here, yep, exactly. This right here is going to be an sp2 carbon hydrogen stretch right there. And how do we know? Because sp2 is usually carbon double bond and then hydrogens. It is this CH stretch of this carbon double bond that has a higher energy and therefore has a peak. If it was an alkyne, and Dominic guessed alkyne, so he was actually the closest, yes. It is an alkene, but if it was an alkyne, you would see the peak maybe right around there. So an alkyne would be sp, triple bond, stronger bond, higher energy. So if you don't see either of these two when you see a boring spectra, then it's most likely just an sp3 hydrocarbon. This peak right here also tells me this right there. That is a carbon-carbon sp2 stretch. And it is a very weak but sharp peak between 1600 and 1700 as well. But unless you know that you have some sort of hydrocarbon and you also see this peak to the left of the stalagmites, I mean, that could also be anything else, right? So for example, I'm sure this is something here, but I mean, it's in the fingerprint region. We're not really gonna pay too much attention. So don't get comfortable. Just because something else is iconic and easily distinguishable, don't panic when you don't see the iconic peaks. You can still get some information out of there. If you didn't see those two peaks that I pointed at, you can just tell me it could be octane, it could be butane, it could be blah blah blah. I mean, it could just be any old sp3 alkane. All right. What about this one? What do we see here? What is this spectra here? Well, there are alkane elements, right? We do see that stalactite there, but there's more. What else is here? Very iconic. Can't miss it. Dominic said some kind of carbonyl. Anyone agree or disagree? CO double bond. Excellent. Yes, yes. Awesome. Awesome. Yes. So, yes, there is carbonyl. He is back for those who missed him. The carbonyl is right there. This is our carbonyl peak. I also want to take this as an opportunity to note that spectra are subject to human error and instrument calibration, right? Sometimes you'll take a spectra and you'll notice the baseline is somewhere at like 90% rather than like 95 or so. The closer you are to 100, the better your baseline. But sometimes that's not the case. Either the instrument is old or it hasn't been calibrated in a while. So don't always assume it's always going to be at like 5%. Like maybe some of you guys saw this and you're like, well, that's at 1700, but carbonyls are usually down here. Well, yeah, but if the instrument is old or something, we still have to, kind of look at exactly the number. I told you, carbonyls are going to be in the 1700s, like almost every single time, and they're always going to look something like this. So if you see this and you guess carbonyl, you're most likely going to get it right. But you have to make sure that it's relatively strong. Like if it's right here, that's definitely not a typical carbonyl signal. That's probably something else. So this is definitely carbonyl. And we had Dominic and Tony both arguing for an ester. Tell me why. Why an ester? Why esters? 1200 peak. Okay, so we're saying that this peak right here is probably a carbon oxygen peak. Yes, it is. It does fall within that region. It is very likely that. But this is also one of those examples where unless you know what you're looking for, you can't really tell 100%, right? What else do we see? What other type of carbonyl could it be? I'll give you a clue. Look at this right here. What is that? Well, we know that that region is usually what? That region, those stalagmites are usually what? sp3, sp2, right? But specifically, it's carbon hydrogens, right? These are our carbon hydrogen stretches in this region. Carbon hydrogen stretches. This one's a little bit lower. So, I mean, it could be that the molecule looks like this, right? It could be like, and that one right there could probably be this carbon hydrogen stretch, and the molecule could look something like this, for example. Or it could also be an aldehyde. And on the other side, there might be an ester. Remember, this doesn't tell us the number of functional groups present. It just tells us that they're there. And if you have two functional groups that often have similar signals, it might be difficult to tell. So in this specific spectra, you could argue that the carbonyl is an aldehyde, because then you could say, well, this is just another, pointless peak that we don't really look at. But this peak is very characteristic of that carbon oxygen. You could also argue that it is an ester. More information is needed. This could also very well just be, for example, that right there. It doesn't necessarily have to be this aldehyde CH3 stretch. It's hard to tell. It's not definitive. We just know that there's something going on there. This is one of those examples where you need to know the structure that you're expecting, or you would just go and take an NMR and then get even more information for the structure. You can't simply guess the whole molecule simply based off of one structure. Does that make sense? So you can make the case for both. The answer here would be more information is required. The one thing you can claim for sure is you have that carbonyl present. All right. Any questions about this spectra here? Okay, what about this one? What do we see here? What is the spectra here? Okay, we see the stereotypical CH stretches, right? What else? Or should I say anything else? Okay, maybe aromatic group, right? We have this peak over here at 1500 or so. I believe most of the aromatic peaks do show up a little bit like around this region here. Like you might see something very small and very sharp. I mean, you could also make the case that this one is there. So maybe, perhaps, right? See, this is one of those spectra where, I mean, we can't really tell much else other than it's just a hydrocarbon. So this is some sort of hydrocarbon. These peaks here, it could be an aromatic slash sp2 hydrocarbon, but I mean, I also don't see a peak right over here, right? If it was a carbon, double bond carbon with a hydrogen, you might see a peak a little bit to the left of the regular 3000 peaks. And you might also see a peak right over here. So I mean, it's very likely this is just an alkane. I don't claim that that is the right answer. I know it's a hydrocarbon of some sort. You can make cases for most of it, but absent some very defining peaks, all we know is there's not really any functional groups in here. And that's just as valuable of an information because if you're starting with something that has no functional groups and you're trying to put functional groups on it, and then you see this spectra, you're like, well, I messed something up. I did something wrong. I have to go back and start again. My synthesis was not a success. And Tony said, kind of basic. Yeah, pretty much. So yeah. So again, you need to kind of just look at the overall clues. And the more you do this, the better you will get at it. And I will show you how to practice these at the end. Okay, unknown five. What do we see here? Yep, exactly. Exactly. Yep. People are getting the same answers, which is good. Yep, exactly. So you see right off the bat, you have a broad signal. Here's your broad signal. And then you have two peaks to the left of the stalagmites, and therefore this is a standard NH peak. You have two signals, so it's NH2 primary amine right there. Very iconic, you can't miss it. Looks like a peninsula. The number of peaks tells you the number of nitrogen hydrogen bonds. Is there a carbonyl here? Is there a carbonyl in this molecule? Dominic says no. Agree or disagree? No, you can't say maybe. Come on, man. You gotta make it. You can't be like, well, there might be. Okay, I got two no's. Science. Yes, what kind of science? Be specific. All right, so we got two no's. Any yeses? Does anybody think there's a carbonyl? Or are you just like worried now? You're like, well, they already said no, so I don't want to say anything. Well, the answer is yeah, there is no carbonyl. There is no carbonyl. Even though there is a peak here roughly at 1700, this is a very not intense peak. This is a weak, I would say, yeah, kind of a weak peak. And also look at the baseline, right? The baseline is kind of like right here. So you have to also kind of take the baseline into account. This is not a very strong peak. This is definitely a weak peak. So even though it is at around 1700, a real carbonyl peak would go all the way down over here, or at least around 20% or so. So this is strictly just an amine spectra. You can, once again, you can kind of make the claim that there's like a nitrogen carbon somewhere around here. I mean, that could be that could be this. We know it's there. So if the peak is lower, would it be a carbonyl? Yes, correct. If the peak, the proper way to say it is if the peak was more intense. So percent transmittance, the lower the transmittance, the higher the absorption, the higher the intensity. So if the peak was more intense at 1700, then yeah, you can make the claim that that is a carbonyl present. Remember, carbonyls are very distinct. Like you know it when you see it. That doesn't look anywhere near like any carbonyl that we've seen so far. So I would not call that a carbonyl. And also, it's relatively sharp as well. I know I kind of blocked it off with some of the drawings, but let me see if I can. No, the drawings stay. But anyway, yeah, that's a very sharp peak. Carbonyls tend to be a little bit more rounded. So that's why. So for sure, there is an amine here, specifically primary amine. And then what about this one? This is a very bad spectra, by the way. Like, look at that baseline. That's at like 50% right there. Okay. All right. I'm getting some good answers. Yep. Remember to use proper names. If we have to call it what it is, right? Everybody wants to be called by their actual name. Exactly. Excellent. Yeah, carboxylic acid. Carboxylic acid. And again, this is one of those examples where like the spectra is not gonna be very high resolution. Like maybe this is an old instrument, maybe this is a first time person taking an IR, or maybe the instrument just needs to be updated. Whatever the reason, you see the baseline is already kind of funky and off and a little strange. So with that in mind, we still have to see if we can identify anything. Just because we don't do something correctly or something doesn't come out the way we expected does not mean we cannot still get information from it. We can still learn something. So if you look at this peak right here, that corresponds definitely to a carbonyl peak. And this is an example of what I mean when I say it's iconic. You kind of see two peaks here. I'm going to just blame the resolution of this spectra here. This is still a carbonyl peak. It's a very strong intensity, very strong absorption. And then the fact that this whole signal is broad from 25 to 35, that is very iconic of carboxylic acids. And, if the resolution was better, you would probably see the little scruffiness of the beard here at the bottom. But that is still a beard. That definitely looks like a beard. If it was only just an alcohol, the signal would be shifted more to the left towards the higher wave numbers, and it would be a lot more smooth. It would look something like this if it was only an alcohol. And then over here, you would actually have your stalagmites right there. But since you notice the signal is even broader, plus you have your carbonyl peak, you know for sure that this is a carboxylic acid, even though the resolution is not very good. And then if you want to just confirm it even more, you could also say, well, look, that peak is most likely a carbon oxygen peak right there. Does that make sense? All right. And I think this was our last unknown. Yep. So you see here we have our table. So we don't expect you guys to memorize where things are. We all use tables. I'm pretty sure you're gonna be given a table in the final. I'll double check, but it is still a good idea to kind of have these numbers in mind. Where are these things going to be found? Where are you going to see these things? Single bonds on the lower end, double bonds a little bit higher, triple bonds highest energy, polar bonds higher energies, aromaticity weakens bonds, so a little bit lower, things like that. So these are some of the things to keep in mind. I would advise you to practice your problems, consult this table, and you can also compare to actual known spectra of compounds. And that is what I am going to finish with here. So before I move on to the final part of the presentation, are there any questions about what we just talked about? Anything you want clarified? Anything you didn't quite understand? Anything that you want me to like talk about again a little more? Okay, so I'm going to stop sharing the screen really quick. And then the last thing I'm going to show you is I'm going to show you a website where you can use IR spectra of known compounds to practice your IR skills. So I have to find the website real quick. I forgot to pull it up when it was time earlier. And now my keyboard is not working. Wow. Okay, let me pause the recording one more time here, and then let me try to figure out this. Okay, we are back. So this is the last thing I want to finish with today. Today, we talked about IR, we talked about what it is, we talked about the spectra, how to use the information to identify compounds. This is a database where you can look up the compounds that you plan to synthesize, that you are currently working with, and you can use this as a standard of comparison. This website is called the Spectral Database for Organic Compounds. I learned about it when I took organic chemistry. Now I am passing it on to you. It is a Japanese website that compiles spectra data. You do NMR spectra, IR spectra, mass spectrometry. Some people have gas chromatography, all sorts of things. So you make sure that you save this for your use. I encourage you guys to look up compounds that are interesting to you, or perhaps compounds that we've worked in class. Like we've worked with acetaminophen, we've worked with salicylic acid, we've worked with methyl acetate, dichloromethane, all sorts of things. So when you go to this website, I agree to the disclaimer, and you will see you can search for things. You can search MS, mass spectrometry, you could search carbon NMR, Raman spectroscopy, um, elemental spectroscopy, radiation analysis, whatever that stands for. Right here, I'm going to click on IR because I'm only interested in IR. And so, for example, we've been working with acetaminophen, right? Acetylaminophenol. So there's some functional groups on there. Acetaminophenol. Let's look it up. Acetaminophen. And then you go ahead and click search down here. And you're going to see right there in the results, you have acetaminophen. And you see under IR, you see Y. That means yes, it's available. So you're going to click there and you're going to see right there the beautiful IR spectra of acetaminophen. So look, you have the structure down here. Remember, it's wrong or not right, or we're never going to give you a spectra without a structure to at least guess what it is. But they give you the structure here. You see that OH? So you come over here and you can find out, is there an OH? Well, not exactly. So we'll talk about that in a bit. What about that NH? Do you see an NH peak somewhere? Anything that you could assign to NH? If I gave you this spectra and you didn't know this was acetaminophen, or I told you, it's acetaminophen, point to the peaks. Can you find an NH peak here? It doesn't look like the usual NH peak, but it's there. The NH peak is actually right here. Let me see. I wonder if I can draw. No, not now. I can't draw. I don't know why. But anyway, if you look at, let's see, this is 3,500. If you look at around 3,400, there is a very sharp peak. That is actually our NH peak. The reason it's not broad is because you're having this conjugation aromaticity delocalized effect as a result of the fact that you are attached to a benzene ring. Remember, when you have benzene, that's when things start going a little bit crazy. So, oh, I figured out how to get the pen back. Okay. So this right here, this is going to be your NH peak right there. And so the reason is this has a resonance structure. And then if you have your N right there, you could have a double bond to that nitrogen right here. You have that H, and then you have that carbonyl CH3. If you have that double bond with that hydrogen here, that double bond changes the strength of this single bond attached to this nitrogen down here. And then, of course, you have your conjugated ring. And then on the opposite end, you have this oxygen. Because of resonance, this oxygen will sometimes also have a double bond. So basically, this whole system from here to here to here to here to here, and then to here, this is all one conjugated system. That is going to drastically change the signatures, the intensities of all of those functional groups in that alternating single double bond. That's why we do have to keep conjugation in mind. That NH is still present where we expected, it just doesn't look like what we were used to anymore. This right here, this is still our CH3 stretches. Probably from this singular one right over there. That's why you don't see it look the standard way that it looks. And you're probably gonna ask me, but wait, what's happening with this OH? I don't see the broad peak that you're talking about. Right, because sometimes that OH is gonna just be a double bonded oxygen. That, by definition, is no longer gonna be an OH. You're gonna learn about this later on in organic synthesis. It's called enolization. Like you have a double bond oxygen, carbon oxygen that turns into an alcohol, and vice versa. And that can happen in conjugated systems. So that's the reason that this signal disappears, even though there is an OH there. What about this peak here? We all know what this peak is. What is it? What is that peak? Tony says carbonyl. Do you guys agree or disagree? Exactly. Yep. So again, very sharp. It's around 1700, a little bit lower. Why lower? Because conjugation weakens bonds. And when you have a weaker bond, you go to a lower wave number. That's why it's not exactly at 1700, but it is still very strong and distinctive. So this is an example of how the real molecules differ from the examples. We gave you the easy examples that only have a single functional group. I'm showing you how you can use real spectra and the knowledge that we just gained, plus also knowledge of general organic chemistry to justify and identify peaks, even when they don't always look like what you've seen so far. So this would be the example spectra for acetaminophen, and this is what it looks like. You can look for it as well. Let's do one more. Let's do one more spectra. So I'm going to go ahead and click back. We've been working with salicylic acid. So let's go ahead and look at salicylic acid. Is it salicylic acid? Yeah, there we go. And then I'm going to go ahead and click search. And then there it is. It's the first response, salicylic acid, IR spectra available. I'm going to click yes. And here it is. Wow, look at that. So here's another example of a real world actual IR spectra. The other ones were too, but this is a bit more complicated. So again, we have that aromatic ring. So that is going to already change some things around. Additionally, we have an oxygen connected directly to the ring. And then we also have that carboxylic acid that is directly connected to the ring. Do you guys see the beard? Do you see the beard of the carboxylic acid? A little, right? Yeah, it's not as iconic, but if you notice, again, you're over here, you're at 2500. So here's 2500, and then look at the broadness of the whole thing, right? from 2500 to around 3400, 25 to 34, that's almost a 1000 wave number difference. It's 900, but it's almost 1000. That is very typical of carboxylic acids. And it also helps that we know the actual structure, so we can use that to justify what we're trying to say. You'll find that a lot of science is you do experiments, you get results, and then you try to justify in hindsight. So this is definitely a broad peak. It looks definitely like some wizard's beard. So this is definitely your carboxylic acid beard. What is this peak right here? Exactly. This is our carbonyl peak. This is our carbon double bonded oxygen peak right there. It's roughly at 1700, but again, you have a conjugation effect. See? Double bond, single bond, double bond, single bond, double bond. That is going to weaken the bond. That pushes it below 1700. 1700 is right here. This is roughly at like 1650. Why? Lower because of conjugation effects. If you have conjugation, the bonds are weaker, the wave numbers are usually smaller. And then, since you have this OH right here, well, you also have another OH that is part of the carboxylic acid. Those signals are blending into each other. And also, this is a conjugated alcohol. So you also have a resonance structure where this is a double bonded oxygen, which is basically another type of carbonyl. So you don't really see alcohols in conjugated systems as much as alcohols in systems that are just straight carbon chain. Does that make sense? And are there any other peaks around here? I'm sure one of these peaks right here, maybe this one. This is probably your carbon oxygen peak. And this, well, I don't know what this is. And this is probably, these are probably our carbon, double bond carbon peaks right there. So again, it's not a 100% exact science. We're kind of just looking for the gist. We're looking for the signature shapes of what we're looking at. And then let me see if I can do one more. One more. Oh, I gotta clear my drawings. Any requests? Does anybody want to see any specific IR spectra? We could do THC. Let's see, tetrahydrocannabinol. Ah, well, there you go. The Japanese don't like THC. All right, something else? Any other molecules you guys want to look into? I wonder if they have psilocybin. Hey, Dominic says meth. Let's do it. Called dextromethamphetamine is the actual chemical name. Oh, they don't have it. They don't want you making drugs, so they don't want you to confirm it. Yeah, I know. I'm sad too. Let's see. Maybe if I type it like this. Nope. Yeah, I guess we can't look up drugs. Wow, I never actually tried this. Yeah, I guess they don't allow us to look up drugs. Sorry, guys. Well, why don't we just look at alcohol? I'm sure that's acceptable, right? The Japanese love to drink. Of course. Of course. There it is. So here we go. Let's look at ethanol. They don't have just regular ethanol. Oh, we could do caffeine in a bit, yeah. Oh, they do have it right here. So let's look at just regular ethyl alcohol. IR spectra. Yes. Boom. Hey, that looks a lot more familiar. This is what it looks like down here, right? It's just two carbons with an oxygen. I've been on a list. I'm a chemist. Yeah, Sam says I'm on a list. I've been on a list for many years. But anyway, so yeah, we have our ethanol right here. You see the alcohol right here? Do you guys see the OH? Let me reset my zoom. There you go. Let me go back to the drawings. Click. Okay, so this right here, this is our broad to the left of the stalagmites alcohol stretch right there. And that, of course, corresponds to this down here. And then here you have your general run-of-the-mill CH stretches. And then we have probably our carbon oxygen peaks right here. Something is happening there, but this is definitely carbon. I mean, there's nothing else that could really be, right? Carbon oxygen absorbs strongly, and it's roughly between 1000 and 1200. So this right here, I have no idea what that is. This is probably just some noise, but this is a lot more easily understood. And so you see that the simpler the molecule, the more recognizable the spectra. It's only when the molecule gets very complex that you kind of start like, well, I mean, I'm suspecting that's what it is, but I'm not exactly sure. Uh, there was one more request for caffeine. Let's do caffeine, and then after that, we'll call it a day. So caffeine. Let's see if they have it available. They should. Oh, I have to agree to the disclaimer again. Oh, there we go. Here we go. IR for caffeine. It is available. Nice. Oh, okay. This is a good molecule. Let me zoom in a little bit. Okay. So let's see. What do we have? We have carbonyls and we have two carbonyls. So where are those carbonyls at? Give me numbers. 1700, right. So here we have our first carbonyl at 1700. Where else? We have two carbonyls. 1600, right? So 15, 16, 17. Yep. So around 1650 or so. Yeah, there you go. 1650 or so. That's these carbonyls. Which one is which? I can't really tell you. My suspicion would be that this carbon has two nitrogens around it. Therefore, it's going to be more polar. Therefore, it's going to be higher energy. So I think this one right here, let's call that one number one. I think that one is this one right here. I think that one's number one. And I think this carbonyl here, since it only has one nitrogen, it's going to be a little bit weaker. So that's going to be this one, carbon number two right there. And this is all speculation. It could be completely the reverse, right? I just know that there's two carbonyls and I see two signals because they are in slightly two different environments. What else is here? Well, we have tertiary amines. All of these nitrogens are tertiary. Therefore, there is nothing here. There's nothing here. This right here, this is a carbon double bond carbon hydrogen stretch. An sp2 carbon hydrogen stretch right there. Because you see, you do have an sp2. Oh, it's getting a little crowded. Let me go ahead and clear the drawings. You see that right here, you do have a sp2 carbon hydrogen stretch right there. And I think that's the only one. Yeah. Yeah. So that right there shows up as a peak right there. And so you have your carbonyl peaks, you have your sp3 peaks, you have your carbon double bonded to a carbon peaks, probably this one right there. That's your carbon double bond carbon peak. Maybe that one there. I don't know. You know, again, it's not exact science. And so again, this is just an example of how we actually use IR in the real world. And you don't have to pay attention to every single peak, only the very definitive ones that you are looking for. So this is how we use IR. This is what it is. This is the theory behind it. Please save this website and just practice, go Google interesting things that are not drugs so you don't get put on a list. Spectral database for organic compounds. I've been using it for almost 8 years now. I continue to use it to this day. Not very many people get told about this website. Of course, if you go to the PhD/graduate school level of organic chemistry, you do know about this website, but you know, most of the times this is not really necessary for you guys to pass the class. But it is very good practice. I highly recommend you use the website. So I'm gonna go ahead and stop sharing the screen now. Are there any questions before we finish today? Okay. Well, if you guys do have questions, feel free to stick around. I'm going to go ahead and pause the recording now, so I hope you guys all have a good weekend. Thank you for coming today. I will be posting this on Canvas, so also be on the lookout. And I also have posted the one that I did on Wednesday as well, so you can watch either one. But thank you guys for coming today. I really appreciate it. I hope you have a good weekend. Make sure you read up and do the procedures for Lab 5. That is a real lab. We will be doing that next Friday. And there is a pre-lab quiz. And there is also a post-lab IR quiz as well on that same day. So make sure you keep studying your IR, complete your IR stuff from your lab manual, turn it in on Friday. Other than that, thank you very much. I hope you guys have a good weekend, and I'll stick around in case anybody has questions.